spotlight research presentation come to an end, we will be presenting to you our. Oh, sorry. Yeah, we will be coming up next the segment of reasoning and intelligence, dedicated to showcasing the top 10 research presentations selected for their groundbreaking contribution to the AI community. And first off, we're gonna have Gemi. Gemi Wallowit. Nice to have you with us here. How are you, Gemi? It's okay.
Very.
Perfect. You
I'm
can
good.
hear.
I think I have some issues sharing. Maybe the next person can go first. I'll have to restart the browser, I guess.
No problem. Okay, so next on we're gonna have Stefan or Stepan Tarantico.
Yeah, Stefan.
Did I
Thank
spell
you.
your name right? All right, the stage is
Yeah,
yours, and I'll be muted. Thank you, and you're next.
thank you. Uh, okay, I hope you can see my screen now. So yeah, I'm so excited to be here today. Thank you for the invitation. And so I'm gonna present you our work on the transformer models, specifically the new framework, which we call context attribution space model framework. And what we see from the results that we've obtained with this research, we see that it improves generalizability and stabilization of the fine-tuning of large language models. And hopefully we can review our results today and just prove you that this is a working framework that can be used in the industry today. So a little bit about few words about motivation and why do we even need that. So first of all, the domain of large language models is developing super rapidly. I don't think that I need to emphasize that much more than that, but we all know that it's developing super fast. The particular strength of the large language models and why they're so good is that because they are generalizable quite well and they are very accustomed to different tasks in a zero-shot manner. But what is bad is that pre-training stage is very costly and it's very inefficient to just repeat it for every downstream task, because when we go from very broad domain to a very specific domain, we want to fine tune our model specifically to that domain, and we want to make it as efficient as possible. But however, with current techniques and approach that we have in the state of the art, it doesn't produce the results as if we adapted the model completely, so trained it completely. And we are trying to bring our framework to deal with this issue and so we want to have a right balance, right trade-off between having the model very powerful for the specific downstream task, but also still be generalizable. And I just want to give a little example or preamble for that. So we had one Kaggle competition, and the model that took the first place, I guess it was a couple of years ago, the model that took the first place had around 98% of accuracy on predicting the fake with non-fake news. And so it was the first place they took the prize. But then we tested, so we reproduced all the results, we tested this model, and just replaced the data set from one fake news data set to another fake news data set, and it fell immediately to almost random guessing. And this is a major problem because this approach is so badly generalizable. So our proposal is the space model, which is basically an external framework for efficient context attribution. And I'm gonna explain what's context attribution just on the next few slides. But the good part about this one is that it can be used with any transformer model. Moreover, it can be used with anything that provides embeddings to the further framework, to the further space model. It basically plays the role of the pipeline's original downstream task head. So whenever we train specific head for the specific task, we just replace that head with our framework, and it just improves the performance. That's our claim. So basically, we can take any language model that exists today, and whatever benchmark performance, but whatever task it has, we claim that with replacing the final head of this model, we still take all the potential of this model, however powerful it is, and we just apply an additional context attribution layer, and it just improves the both performance on the same downstream task, but also maintains very great generalizability and stabilizes the performance. For that generalizability, we also introduced the intraspace loss. That's an auxiliary loss function that just stabilizes the performance, and it ensures that the concepts inside the context attribution are not collided together, which will make sense in a minute. So just to give you an idea of the data sets and the benchmarks that we tested it on the social media attributions of YouTube comments. So basically there was a Chennai water crisis in India, and they tried to do something very similar. So they tried to employ the context attribution from the social media comments on YouTube to the language model to improve the performance, to enhance the prediction capacity. And basically, they were trying to do what we are trying to do, but in a bit different way, more supervised, while we are doing that completely unsupervised. Then we have the Hate Explain, very famous data set, which classifies the hateful, offensive, and normal tweets, I guess, and also the IMDb movie reviews. So basically, the last two, as you can see, they're from somewhat the same domain in like kind of sentiment analysis, but not really. And we test them cross data set on each other, and that's how we prove that the model is so well generalizable. That's how we claim that we can show that it generalizes not only for the specific data set for the specific domain, but inside cross domain. So a few words about what's context attribution. I need to get some specific naming here. So we call the contextualized embedding whatever is the representation of the input that is provided by the base transformer model. It is as simple as a set of vectors, where each vector is just an embedding of a specific token. That's all it is. While the context attribution is a projection of this collection of vectors onto the concept spaces. Just a high-level idea, what is the concept space? The concept space is basically all the set of synonyms or the concepts inside a specific domain task. Just a simple example. Let's say we have a problem of classifying hateful and non-hateful comment on Twitter, for instance. So we have two concept spaces. One of them is hateful concept space, and another one is non-hateful concept space. And whatever represents this concept space is called the contextualized, like concept inside that concept space, contextualized embedding. And basically, context attribution is taking the contextualized embedding from the transformer model and projecting that embedding into the concept space of the specific concept that we are trying to describe. For the hate problem, we have the concept space of hate and the concept space of non-hate. It will make more sense when we get to the diagram how it looks like. But basically, for each class, we assume that there is a single concept space operator. This operator is trained during the fine-tuning process. So basically, we can just, and it's super, super small. That's the whole point of it. It's super efficient, and you can just train it without any adjustments to the big large language model behind it. So yeah, it's optimized during the fine-tuning with that specific formula that we see right here. And here's why that is that way. So we have the loss function, which makes sure that whatever concepts we have in the concept space, those concepts do not collide into a single. So let's say we want to describe the set of all the possible concepts that describe hateful concept space. And we want to make sure that not all of these concepts just collide to a single concept. So that's why we need this intraspace loss. It makes sure that all of the concepts are divergent inside the single concept space. And this is basically just an inverse of the variance of the metrics, of the transformation metrics. It's just a simple variance. And then we also add the cross entropy loss for the specific task classification. Here's the architecture that I was trying to explain to you. So basically, here's the main part, the transformer, which just produces the embeddings. Then there is the hate concept space and non-hate concept space. That can be any number of concept space, basically. It can be 10, it can be 15. It's just for the simplicity we show to here that it's hate and non-hate. And the intraspace loss makes sure that all the concepts inside that concept space do not collide. And then there is a space mixer, which just takes all those representations from different concept space. It mixes them, which is basically just a fully connected layer or a set of fully connected layers. It mixes all of them, and then based of that makes the prediction for the final model. That's as simple as that. Here are some of the visualizations that we have of context attribution, basically. So for this one, we have the negative and positive sentiment of the IMDb review. So basically, what we see here is that in this specific concept space, we want them to be orthogonal because they are from different representations. They are from either negative or positive concept space. So we want those representations to be orthogonal so that we can easily distinguish between them. And here is a bit more complex example that's for the hate classification. So it's either offensive or hateful or normal. And we can see that some of them are orthogonal while others are a bit less orthogonal and more collinear. That's because hateful and offensive, for instance, they're in somewhat similar position. They're somewhat similar, but they are still very disjoint and orthogonal. That's what we want to achieve with this context attribution. Here are some brief results that we obtained. So we see that we compare our model with our layer with different base models. We call it base model. Whatever model produces the embeddings, this is based. So basically it can be any kind of language model, but we use here specifically DistilBERT, BERT, and XLNet. So for this one, you can see some results here. And also the most prominent results is probably this one. Oh, sorry. It's probably this one, because for the XLNet model, this is the model that has the current state of the art for this data set. And this is the best result that we could reproduce with that model, with all the approaches that we tried. And without any changes to the parameters, without any variation of our model, of our parameters, this is the result that we obtained just by applying our space framework. This is what we want to show, that how well it improves the performance compared to the baseline that we currently have, and how well it performs compared to the state of the art. And this is our deer shot example. So when we train on one data set, here we train on the IMDb, and then we test it on hate explain, and we show that while the XLNet model just puts everything into accuracy and forgets about the recall, so basically just predicts everything as one class, our space model is still doing very good and doing the good job, having the high F1 score and having the high balance between precision and recall scores. And this is the final but very important part. Here we show the stabilization of the performance. So as we can see on the left plots, those are all the trainings of the basic models. So basically like DistilBERT, XLNet, BERT, those are all those models. That's how their curves look like. This is the loss, this is the accuracy, F1 and precision. And on the right, that's how it looks like for the space models. So it is much more stable, it is much more reliable, and that's what we see. Like there is no such fluctuations as, for instance, here, and there is no such divergence as for the loss here, for instance, between train and validation. It's pretty close, it's very reliable, and it's very stable. So basically here are some short conclusions and key deliverables of this project. Is that experimental results on 3 data sets, hate explain, IMDb, and social media attributions, show that this is the model currently superior to all the baselines that we have. It not only produces the superior results in terms of accuracy and F1 score, but also generalizes better cross data set. It is implemented and provided open source on GitHub. So whoever wants to use it can just try and use it for their downstream task and see if it improves the performance. And our claim that it will. And there is also a loss function that helps to attain this generalizability, basically, and helps to produce those results. I guess that's it from my side. Thank you very much for your attention.
Thank you, Stefan, for this amazing session. And it was a really great talk. Highly appreciated. So upcoming and next, we're gonna have Gimme Walawit with us. I hope I spelled your name correctly.
Yeah.
Perfect. So Gimme, the stage is all yours now, and
Okay.
can't wait for what you're gonna present with us.
Let me share my screen first of all. Okay. Can you all see everything? Fine.
Yes.
As a
Now it's
slideshow, I
loading.
guess. Okay.
Yeah, now
Okay.
everything is clear. Everything is perfect. Thank you.
Okay, thank you. So I'm going to be talking. My name is Gimi Valavata. I am a postdoc at EPFL right now. I just finished my PhD last year. Anyway, so today I'm going to be talking about my latest project as a postdoc. So the idea here is extracting human interpretable structure property relationships in chemistry using explainable AI and large language models. And I'm pretty sure everyone here is like super familiar with large language models, maybe XAI too. But in case you're not really familiar with XAI, maybe this can work as like a brief background to explainable AI. All right. So one of the biggest, I'm sorry about these slides being super unclear because I just imported this as Google Slides from PowerPoint. Anyway, now the idea in chemistry, as you can see on the right-hand side, is that one of the biggest challenges is that once we have molecules, how do we understand the relationship between molecules and their properties, right? For example, if we have a molecule like this here, how can we predict its solubility, toxicity, like its binding affinity, and so on? This has been one of like the long-standing challenges in chemistry. Now we know deep learning, machine learning actually helps with predicting properties, or else understand like mapping these molecular structures into a certain like their properties, right? Like although deep learning is really good with this, they are not readily interpretable. By that I mean that yes, of course we know the weights and biases of this function, but these actually don't tell us, don't give us chemical intuition. One of the other things with this is that explainable AI is that most times what explainable AI does is that it actually helps us to uncover the black box nature of these deep learning methods. This is a relatively new branch of AI, but the idea is that it helps us to understand the rationale behind a certain prediction from a model. Now, although the intended use of explainable AI is to assess the model performance, in this work that we are using here, we use explainable AI as a way to uncover input-output relationships. Now, yes, explainable AI can do that, but most these methods are developed for technically oriented users or model developers. So they are, again, not really interpretable. And also these like the outputs from an explainable AI model, it just tells you like gives you some statistics about the model performance, but these do not give scientific explanations. So that's where we thought maybe we can use natural language to bridge the gap between all these components I was just describing. And something I want to highlight here is that although deep learning is really good with like solving challenging tasks in chemistry, chemists are almost always experimental chemists, to be specific. They're not trusting of these deep learning models that we develop, and that is what explainable AI helps us to bridge this gap. But actually, if we can use natural language to actually facilitate, like generate more accessible explanation, that would be we consider that to achieve our main goal of this project. So we know that although LLMs are super good at generating text, but LLMs in isolation are limited to addressing domain-specific problems. That is why now we see a lot of LLM agents with access to external tools. So Expert AI is one such agent that combines explainable AI with large language models to explain structure function relationships from raw data. Okay, now let me give you like a very brief overview of the workflow. Now, what happens is that the input to like the first step of this pipeline is you input a raw data frame. So ones and zeros with labels. And then we fit a explainable AI method like SHAP or LIME or a combination of both to understand which input features were most impactful towards the label. So that is, for example, it's like saying like if we have a hydroxyl group in a molecule, that makes the molecule more soluble. Now, once we have identified the impactful features from the explainable AI method, we combine that with literature and with an LLM, which actually extract scientific evidences to support the claims from the explainable AI method. Actually, that is another way of saying I use the LLM as a RAG model in this case. So once we combine the impactful features which we identify with the literature, with our RAG model, it actually generates a comprehensible, like an interpretable structure-function relationship backed by scientific evidence. Okay, so why expert AI? Why not just using LLMs like ChatGPT or like GPT-4 or like just using a RAG model? The main reason why we suggest expert AI is that it is able to generate targeted explanations for data sets that we provide. Now, with an LLM, like with a RAG model, just LLMs and literature, it is not able to understand like the raw data that we have. It would give you a broad explanation to a certain query that you ask. That is why we suggest expert AI, so that it actually ticks all the labels that we have given here, that of course it generates an interpretable, accessible explanation to non-technical users, and also it provides scientific evidence, and also it generates targeted explanations from our raw data sets. Okay, so to generate the results in this case, in this study, we conducted 5 case studies. That means I used 5 different data sets or data frames in this case. For example, the first case study is like it's a classification problem which tries to understand the presence of open metal sites in MOF or metal organic frameworks in chemistry. And the third one here is like predicting solubility from small molecules. That is also a classification task. The fourth is predicting solubility of molecules, which is a regression task. And the fifth one is another regression task, but this actually serves as a negative example. Okay, I know it was a lot of this output is a big chunk of text, which is actually an explanation. So just basically the idea is that it would tell me which features were extracted by the explainable AI analysis, and also it would tell me that what other features that the literature suggests to be impactful towards what we are analyzing in this. And then one of the other advantages is that this also tells us which references were used to generate this explanation. This is really useful in a setting like chemistry, because always we are trying to understand, like it's like studying for a paper, or like this is like a way of mimicking what a scientist does in a lab. Okay. We also have developed a Streamlit app so that anybody can use it. Hopefully this video can be played here. Okay, never mind. Now this is like the front end of our Streamlit app. You have to give an open AI key, because in the back end we run GPT-4. So you upload all your data sets along with like the literature data that you want to extract the information from. In case you are not sure which literature, like which scientific journals or like articles to use, you can actually ask the expert AI to scrape archive and using some keywords, and then generate a scientific explanation as well. Unfortunately, this video is not playing, but however. Okay, now once for all these 5 case studies, we generated explanations, and we wanted to evaluate if these explanations actually make sense. So we asked 5 human experts to compare and evaluate these explanations from expert AI, ChatGPT, because we use GPT-4 in the backend, and SHAP. Now, why do we compare expert AI with just the language model and SHAP? Because expert AI is a combination of the two. As you can see in the middle plot here, the mean expert scores, it actually tells us that expert AI actually combines the advantages of both just using chat and just using a large language model. That was the main intention of this whole idea of this project. Now, as in the fifth case study, which was a negative case study, of course, it fails miserably. That was expected. The reason why this fails was we did not have enough data to train a surrogate model which goes into the explainable AI method. So that is why it actually does not understand which features were important towards the final target because of the failures in the surrogate model. Okay. Once we generated the explanations, we also wanted to see if these explanations were consistent if we generated it multiple times. So what I did here was generate for each case study, 5 explanations were generated, and we computed the Rouge L metric to see compute the variability of these explanations, and compare that with the GPT-4, the ChatGPT explanations here. As you can see, the mean Rouge score is of course higher in expert AI compared to just using ChatGPT. What we wanted to show here was that since expert AI also is a RAG model on top of explainable AI method, this reduces hallucinations within the large language model. That is why you don't see many variations in the Rouge within the generated explanations, basically. Okay, in addition to both of these evaluations, we also asked another LLM to evaluate different explanations between just asking ChatGPT to explain a structure-property relationship versus expert AI explanations. Now, based on that, out of 5, for 4 tasks, Claude AI was able to actually score expert AI explanation higher than the ChatGPT because, of course, it is a combination of not just a large language model, but also an explainable AI method. In most cases, Claude says expert AI explanation is better because it is able to generate a very specified explanation rather than a broad explanation. So that was the whole idea. Now, with these evaluations, we were happy because these actually tick all the boxes that we wanted. We wanted to generate targeted, interpretable explanations. And with these, we conclude that we have actually achieved our goals. Now, initially, now the whole idea was to make science more accessible, right? But all the results I showed you were from GPT-4. That means you need an open AI key. Now, however, we also tested with open source LLMs, and we were happy to see that we can actually compare these new open source LLMs with the GPT-4, and that is a really good indication that we are going in a good direction with these open source LLMs. And so right now we only have GPT-4 in the backend, but the next step is, of course, allowing the users to use these open source LLMs of their preference. Right. Now, with that, I want to say that here in this work, I present expert AI, which is explainable AI method with the combined RAG model to generate a structure-function relationships in chemistry. Or actually, this can be applied to any domain if you have a labeled dataset. With expert AI, the novelty is that we leverage the advantages of explainable AI and LLMs to provide task-specific, intelligent explanations backed by scientific evidences. Since we use LLMs as a RAG model here, we are able to reduce hallucinations and generate more factually correct explanations. Of course, the quality of the explanation can be improved with more data, better literature, and also by integrating, right now it only has one type of surrogate model, but of course, if you use more complex surrogate models also, you can improve the explainability of these, the quality of these explanations. And finally, we can be optimistic about open source LLMs in place of proprietary models. And yeah, with that, I would like to conclude my talk, and hopefully this wasn't too much of a mess. All right, thank you.
Thank you so much, Gimme, for this amazing session. It was really great having you here with us and very insightful, very actually it's the opposite of messy, very what I would say, entertaining. I enjoyed it personally.
Thank you.
Thank you so much, Gemi. And up next, we have our upcoming amazing researcher and going to be next on stage is Agbai Tabak. So, Agbai, how are you?
I'm fine, thank you.
Good. So, the stage is all yours, Agbai. And yeah.
Thanks.
Yep.
Let me share my screen and I will jump in. Hi, everyone. Today I will be presenting one of the model we are developing at FryLabs, FryLT. I'm a physics engineer and I'm working as a developer at Bytro Labs and the founder of FryLabs. FryLT model is a improved transformer architecture, and I will skip these parts where I explain what transformers are. I think everyone is familiar with them. But let's talk about the motivations. Where do we see improvements for transformer models? One of the main problem with the current transformer models or language models are their size. The hardware limitations are the bottleneck most of the time. For example, there is no consumer setup for running 70 billion model Llama model in the market at the moment. So this is blocking the accessibility for many of the large models, which can represent some emerging abilities like the state-of-the-art models. And another motivation is Chinchilla paper were suggesting that we are underutilizing the transformer models. We are not using the weights efficiently. It was suggesting to train them longer or efficiently, but still that idea of under training gave us other approaches. I will explain it in the next slides. And another motivation was some of the studies show that for solving complex multi-step tasks problems, we need deeper neural networks instead of even if we have same number of parameters, instead of having shallow and big networks, we need deeper models to longer train the models, longer evaluate the data and process the signal. Another motivation was this is not a this is just an intuition actually. There is no direct reference, but our brain is not a linear signal processor which gets the data and process and gives from the other side, like language models we have now. It utilizes different regions, and when it propagates the signal, it iterates over several regions, we believe. As I said, this is just an intuition. So in priority model, the parts we introduce here are, sorry. So we introduced an iteration embedding, iteration encoding layer for the transformer blocks, which simply tries to give information to transformer block at which iteration we are in, while iterating over the same block. Instead of just propagating one block and going to others, we loop over the blocks, and while doing it, this learnable parameter, learnable layer, learns how to inform the block itself about the current iteration. So this is one. Sorry. Yes. The another approach we introduce here is instead of iterating on single blocks, we introduce several groups, variant groups. These are consist of several transformer blocks, and we iterate over these several blocks while carrying over the iteration encoding and passing through them. So this is one of the groups which consists of several blocks, as I said, and the overall structure looks like this. So in the final transformer architecture, we have several blocks which are consist of multiple blocks inside and n number of iterations. And when we combine these, we try to address the issues or motivations we mentioned. One of them is depth problem. Like for the smaller models, we wanna have deeper signal analysis, so it thinks or process the data longer. So we aim to tackle with better training problem. We use less parameters here, and we expect it to be trained better. The first problem was the memory footprint, the hardware limitation. So we also aim to address that one by making the model smaller, iterating on the blocks longer. As I said, this brain-like signal flow is just an intuition. It sounds more natural. So this also helps that aspect. And the last one is actually, this is the result of smaller memory footprint. When we have smaller models, even for bigger models, instead of distributing the model on several GPUs, we will iterate on one GPU, means that there will not be overhead of signal transferring from one GPU to other. So eventually this will help in improving the performance of the language models. Runtime performance, not the quality of the model maybe, but runtime performance. So before showing the results, I wanna show one of the study from Google. BERT is well-known encoder on the transformer model, and what Google introduced with Albert was weight sharing, like we introduced in Frialti, with a different way. They share the feed forward and attention layers among the transformer blocks, and they introduce different normalization layers to apply iteration awareness, let's say, how we call them. So here, even though they don't say that they were iterating on the same blocks, they say they share the weights between different blocks and try to make the model smaller. In the later following slides, I will compare the results with Bert and Albert. So this was how they did the weight sharing. So to make the test easier, even though our architecture allows having multiple blocks in one group, we only use one blocks for the initial tests and iterate it over m times. And so we created the model architecture like this. We increased the embedding dimensions from 64 to 1024 and tried out different layer dimensions and layer numbers for standard models and also for variety and different context lengths. This was the initial test. After this, we increased the vocabulary size, also context length, but the results were pretty much same. So this still reflects the performance of the model. And as a data set, we use tiny stories from Microsoft researchers, Eldon and Lee. So for the results, our evaluation metrics were validation loss and also GPT-4 evaluation. Let's start with validation loss. We trained different models for comparing them with our model. We trained 1-layer and 2-layer llama models for different embedding dimensions. And with the increasing embedding dimensions, 1 and 2-layer models showed better results. And when we use our model with 1-layer with 2 iterations, we see that with the increasing embedding dimensions, it count up the bigger model, 2 size bigger model. And this also, we could also repeat these results with 4 and 8-layer models. So 4-layer model, again, with the increasing embedding dimensions, it gets better. It shows better validation loss, and also 8-layer model show the similar pattern. And our 4-layer with 2 iterations model again count out the bigger model around 1024 embedding dimension. So this shows that this approach, sharing the weights and iterating over on the blocks, actually helps, and model can learn better results, gets better results. And the second metric we use was GPT-4 evaluation. So this includes asking GPT-4 to evaluate the output of the models with this prompt. It is simply explaining that this is a result of a homework from a student, and we ask GPT-4 to evaluate the writing with grammar, creativity, consistency, and plot. We give the initial part of the prompt. We give the initial part of the story to our models, trained models, and we ask it to complete the story. And the last sentence is not complete. The completion quality is represented with a plot, and the completing quality of the whole story is represented with consistency, and grammar and creativity is additional parameters. And what we see here is, with only this prompt, GPT-4 actually could evaluate the quality of the models, trained models, very consistently. So what we see here is validation loss against consistency, plot, grammar, and creativity. And for all metrics, GPT-4 could evaluate the data, evaluate the generations very consistently. The smaller the validation loss gets, the better the results gets. But this consistency is actually interesting ability of GPT-4. And a bit detailed results for the same evaluation, GPT-4 evaluations. I want to point one of the data specifically. Here we see embedding dimensions, and the biggest one was 1024 embedding dimensions. And here, this is the standard model, and 8-layer standard model. These are the validation loss and GPT-4 evaluations. And here is the interesting one, what we are going to check. So here we have 2-layer model with 4 iterations, and we see that even though validation loss couldn't catch the validation loss of the 8-layer model, the metrics, the evaluation metrics are better than the bigger model actually. So here we see the average values for the same one, and this shows it better. So with a smaller model size, 4 times smaller model size, we not only count up the bigger one, also got better results. And here I want to compare our results with Bert and Albert. So for Bert and Albert has the different model sizes, but the one where they could get the better results from Bert was so when they had a model slightly bigger than half of the big one, BERT model, and to be able to get the similar results, they iterated over this big block 24 times, and this resulted in 7.8 times longer runtime cost. And for our model, when we have 4 times smaller model and same execution time, because here we have 8-layer model and we have two-layer model with 4 iterations. Here we have the same compute time, and for performance-wise, we got slightly better results. So we are happy to get these results, and hopefully we will train bigger models to get more real life results, let's say, because this model, the data set and model size was very small, so it is not state of the art model, but we plan to train bigger models. Hopefully we will share them later. So that was it. Since we don't have question session, maybe we can meet later. Hello.
Hi.
Yeah.
Okay, so the questions are probably going to be in the Q&A session. Thank you so much, Akbai, for this amazing session, and really enjoyable and beautiful presentation, by the way. So upcoming next, we're going to have Paul Tarau. Paul Tarau, how are you?
Doing good. Hello.
Hello, hello. So we have now on stage Paul Tarot, and he's going to be presenting up next. So the stage is all yours, Paul.
All right, let me share my screen. I have a bunch of screens open. I hope the good one would be shared.
We're with you, no worries.
And I would go with an entire screen. Let's see what happens. Share. Is it all visible, all fine?
Yes, we can see all your screen.
All right, so then let me go to my actual screen here and walk you through this presentation. So we all like full automation, including for, well, Tesla cars, which are kind of automated, but not fully. Full automation of goal-driven LLM dialogue threads. Well, we have the LLM dialogue threads that are nice and interactive, but we kind of like automation, a simple initiator that triggers everything, and then the work is on the side of the LLM, not on the side of the user. So delegating to the machine as much as we can. And let me overview a bit the technical aspects of what we have here. So we automate deep step-by-step reasoning in an LLM dialogue thread in a very simple way. We, of course, use recursion as my background with the elephants can show you, which is from DALI 0, not DALI 1 or 2 or 3, the actual DALI. Recursion is something that's self-similar and works automatically and nice. And we have two kind of nodes here. We have OR nodes, which is instructing the LLM to explore alternatives, basically. And then we have AND nodes, which instruct the LLM to expand details. So with that, we can start from a single succinct task-specific initiator, and then we steer the automated dialogue thread to stay focused on the task by synthesizing a prompt that summarizes this depth-first search that drives the LLM step by step. So we will also want to keep the LLM as truthful and factual as possible. And for that, we use semantic similarity to ground truth facts or oracle advice from another LLM instance that would restrict the search space and also validate the traces of justification steps that are returned. So with that, we get focused and trustable answers. So some of the applications which are basically coming, you will see a bit of details in a minute, from just basically prompt variations. You can do consequence predictions, causal explanation, recommendation systems, or topic-focused exploration of scientific literature. This being probably the most interesting one, although consequence predictions are pretty interesting as well. So let me walk you over the system architecture first and show you a few examples and then dig a bit deeper in the technical aspects. So we have an LLM and we have a user. We have an interface mechanism. They are the interactors. They take care of all the details of talking to the LLM and setting parameters. The recursors are the most interesting layer that actually this is all object-oriented, and it's actually a system that runs. I will even maybe have a chance to demo a few things if it all goes smoothly. The recursors would then do this iterative descent with AND nodes and OR nodes. Now the refiners would be the ones that bring in the oracles, for instance, to make sure that the output of the LLM is contained. And of course, they would rely on an embeddings vector store. And also, we have ground facts that could be Wikipedia pages or reference documents. The result from either the recursor or the refiners, that actually are a superclass of recursors, would go into a set of answers, and I will show you a bit the more specific structure of those answers in a minute. And these answers would, with help of a propositional horn-clause model builder, that's a very simple logic programming device that will be almost self-obvious when I am getting to explain it to you. From there, we get synthesized logic program. So it's a program generator, actually. And those could be studied separately with logic programming tools. Now, just to summarize, the active components, we call them agents, are interactors, recursors, and refiners. So interactors manage the input prompt and the task breakdown. Recursors handle iterative exploration of subtasks. Refiners enhance clarity and relevance of the LLM responses. And in terms of resources, we have the ground truth facts, sentences collected from online sources or local reference documents, for instance. And then we have a vector store that enables semantic search via embeddings of sentences. Our unit is a sentence, so we do a bit of stanza-based splitting of whatever information comes in from the ground truth into sentences. Let me show you a first example now. Well, because it's we're at Super AGI, I said, well, let's pick something related to a scientific concept explorer, and the concept that we will explore here would be there is a prompt that's not shown here, but basically it's about artificial general intelligence. So here you would see an OR node. Artificial general intelligence is machine learning algorithms or cognitive computing capabilities or autonomous decision-making processes. And now we expand each of them as an AND node. Machine learning algorithms would be supervised learning, neural network architecture, reinforcement learning techniques, deep learning algorithm, feature extraction methods, and so on. And cognitive computing capabilities and autonomous decision-making processes, they are also expanded to some level of detail. So that's the Streamlit interface that is actually available, and I will show you the links to it in a minute. So what we can get, this is not yet in the paper, but it's out there and pretty usable. It does a graph of relations extraction. It's kind of a ontology-like relation set, but it explains the concepts very well. You see, this is artificial intelligence, and then hypothetical type of intelligent agents is a kind of artificial intelligence. So you have various relations connecting the concepts that are extracted by the LLM during this recursive process. Now, the logic programming behind all that. I'm not assuming that the audience is familiar with logic programming necessarily, so let me show you very quickly what that is in a very, very simple situation here. So this is our little pet program. A pet is a dog, a pet could be also a cat, a pet could be a snake. Well, would not necessarily recommend the last one, but it's still moderately popular. A dog barks and walks and bites. So you see the AND node here. You see the OR node here. A cat purrs, walks and hisses. A snake hisses, slither, or even bites. So now there are a number of observable things. We call them facts, and we call these here rules. It's true that whatever is there walks, purrs, bites, and hisses. So what could that be? Well, we start with pet, we explore each possibility one by one, backtrack if eventually it leads to a failure. And then we explore dog first, it barks, we look at barks if it's true. No, it's not true, dog fails right away at this point in time. Now we try cat, and purrs, walks, hisses. They're all true, purrs and walks and hisses, and then this becomes true, our pet, via this path that brings us to a ground truth fact via the cat. We try also the snake. Unfortunately, that doesn't succeed here. I explicitly stated here which facts are true and which are false. So that's the underlying model that we would want the LLM to cast whatever interaction it has into. And then, of course, we explore this at a much larger scale than that what you can see here. And then we can use tools to infer the model, which is everything that can be proven from the set of rules and facts. Now, the deep LLM, that's the system actually, is a logic programming, but done differently. SLD resolution is this mechanism that walks over the clauses. Of course, here I showed you just the propositional case, but it works with variables and unifications, which we do not have any need for here. We want to use LLMs at what they are the best. They work with natural language, and we have to avoid doing too complicated logic formulas, although GPT-4 writes Prolog code if we really want to, but at large scale and reliably, which is what we are after here, nothing beats a simple propositional logic model with AND/ORs and nodes and OR nodes. So what we do as we proceed on that in that recursive descent, we do creation of clauses, the heads, and then the bodies, and we create a dynamically a logic program. Now, as the dialogue units are sentences, the underlying logic is propositional. It can be also split into subject, verb, object, or other relational models, and then you can do knowledge graphs and conventional inference, either with description logics or with logic programming systems like Prolog or answer set programming systems. The client-side management happens via the API of the LLM's memory, and is based on goal stack, where you kind of stack what you have to do and explore and do backtracking on it. And then also a goal trace. The goal trace is particularly interesting because it tells you what was the path that walked you to truth in this case. When the depth limit is reached, the items on the goal stack are interpreted as something we call in logic programming abducibles, something that could be assumed to be hypothetically true, but then later, and especially in the case of oracles that could invalidate them, they could fail, and we call that checking mechanism integrity constraints. So we have to keep the ground truth in mind, and our depth-bounded refinement step support compilation of the dialogue threads to this horn clause program to be explored later with logic programming solvers. We have modular task-specific customizable prompt engineering primitives that are aggregated together for end-step and or-step prompts. And we use normalized semantic similarity measures that can be used as probabilities. And there is a branch of logic programming called probabilistic logic programs that associate probabilities to the facts, no need to associate them to the rules because they cannot propagate. And then with that you can do approximate reasoning, and they also have some deep learning models that use probabilistic logic programming. Sentences in authoritative documents would be the ground truth facts on which we can rely. So overall, our approach explores synergies between structured prompt engineering, we just have templates and then they are getting automatically filled out, logic-guided recursion over LLM queries, and semantic search in an embedding vector store. So let me show you some of the prompts very quickly. I don't know exactly the time. I am assuming we're at about 10 minutes because I'm sharing the full screen. Let me maybe splash on the, well, let me just keep it here, not to mess it up. This is a causal prompter. It's just a dictionary. It has a name. And then this is a prompt. We need causal explanation in this context. This is a variable that's passed to the template. We have here a goal that kind of keeps the recursion focused. And here we have the OR prompt. So we need a causal explanation in this context, alternative explanation in this case, and in this case, elaborations and explanation of 2 forwards for each of the causes of G. So that's the model and OR nodes. And then what you get out of that, you get the head here with multiple alternatives, or the head here with conjunction, or multiple elaborations of what this actually means. So very, very, very simple. The embedding vector store can filter the abducible, those hypotheses that we make in the process when we hit a depth limit, with semantic distance to ground facts. So some of them are accepted, some of them are rejected, and that restricts the inference space. refining decisions with LLM-based oracles. We have two of them. One of them is just true or false. It's a decider, it likes it or not. And then we have also a rater that on a scale of 100, which then gets normalized into probabilities, would tell you how likely something is. And there are just alternative instances of the LLM. So that brings us towards this objective, which is to have trustable AI. It's a requirement that's very popular these days for various reasons. DeepLM provides a principled approach towards trustable generative AI. It's also formally verifiable that whatever is inferred from those logic programs, they're very simple formal language, actually. Here's an example of a counterfactual. What if NP would be equal to co-NP? So that's just another example. It would tell you what would happen, revolution in complexity theory, transformation of cryptographic systems. So you see also the quality of the knowledge encapsulated in an LLM. This is generated by GPT-4. In a hypothetical scenario that what would be the consequences of something like this being. That's less popular than P equal NP, but it's still very deep in consequences. A follow-up question generator is an alternative. So the screenshot here would work in a slightly different way. Instead of those entities or simple noun phrases that you have seen before, here we have the LLM generating a follow-up, set in fact a follow-up questions to its own answer. So by forcing the LLM to look one step in the future, you make it more precise in a way. That's kind of an interesting consequence of this follow-up question request. So then the follow-up questions become the ones that get recursively explored, and here is a trace of explorations. How can humans align super intelligent LLMs to human goals and values, right? One of the big strong AI discussions that people are either worried or excited about. So to finalize, how DeepLLM enhances the user's LLM interactions. Well, it reduces the complexity of prompt engineering, automates the composition of tasks into simpler subtasks, refines prompts for more accurate user intent capture, generates dynamic responses for a wider range of queries, and improves the user experience with concise and relevant information. Otherwise, you see that sometimes LLMs hallucinate or become too verbose, or ask for forgiveness for being wrong, even if they are right, and so on. So let me, in the interest of time, show you very quickly some of the models here that you can actually play right away. So this is
sorry to interrupt. We have around 1 minute maybe, so we can close it because we're past the time session. But it's okay. You have 2 more minutes, and then we'll end it. Take your time.
Okay, I'm wrapping up in 1 minute. So that's one of the links. You just activate the LLM, and you would see it in action. This is another link. This would take longer, so I'm not waiting for it, but you see it running. This is basically something that can review a paper or summarize it quite nicely. The links would be all at the end. And let me then show you this is a question generator, also recursive, and they are all at the Streamlit upside. So let me just switch to the first screen and get to the links. And thank you very much for listening. That's it.
Thank you, thank you, thank you so much, Paul. This was really amazing session and very insightful. Really great to have you. And upcoming next, we're gonna have our speaker, Paul. Paul Taro is gonna be presenting next with his session. So, Paul, do we have you?
I
Oh yeah, sorry, it was you. Sorry, my bad.
I can do a repeat, but
It will always be great to have a presentation from you. It's really always great to have a presentation from you. But I believe then next we have upcoming is Zheng Zhao, right? Yeah, Zheng Zhao.
Hey,
We will have you next.
hey, hey.
Oh hey,
Can you hear me clearly?
how are you?
Good. How are you?
Good, good, good. So it's nice to have you here, and the stage is all yours now.
Yeah, let me try to share my screen.
Right.
Can you see my screen?
Yes, we can.
Good. Now I can start, I think. Good. Good evening, everyone. My name is Zheng Zhao. I'm currently in Uppsala University, Sweden, as a postdoc. So my research interests are basically computational statistics and diffusion models for machine learning. So the project that I am presenting here today is concerned with a Feynman-Cast model, like how to leverage a Feynman-Cast model to train Bayesian neural networks efficiently. So we have this work just accepted in the AStats in 2024, and together with Sebastian Meyer, Thomas Schoen, and Ins Hjulund. And takeaway message for this paper is that so all we have done is that we have developed a very efficient, computationally and statistically efficient Monte Carlo method, which we can use to train a very large Bayesian neural networks on large data sets. Okay, so let's briefly recall what is a Bayesian neural network, just to make sure that we are on the same page. So imagine that we have function f, okay, so input x and with output y. Now imagine this function f is a neural network. Now it has some parameter, let's call it phi. Now what is called a Bayesian neural network is that we put the prior on the parameter phi. So the phi will not be some deterministic parameters, but instead it is a random variable or follow some distribution. Let's go p phi, which is a prior. Now the goal of training a Bayesian neural network. See, we have data sets xi and yi. Now the goal of training a BNN, Bayesian neural network, on data sets, it means to compute the posterior distribution of the random variable phi, okay, conditioned on our data. And now, just by simple Bayes formula, this posterior distribution that factorizes as the prior product with the likelihood probability distributions. Now, of course, this posterior distribution is in general intractable because of complicated computation. So in practice, we usually seek for approximations. For example, Gaussian approximations, which we can use Laplace approximations, so we can compute approximate mean, and then we approximate covariance around the mean to form a Laplace approximation. Or we can also use variational Bayes, so that we can approximate the posterior distribution by some parametric variational family of distributions, and then we optimize the parameters of the variational distribution by optimizing with respect to its evidence lower bound. Now, another very promising but not very efficient method is by Markov chain Monte Carlo. So essentially, we're trying to statistically exactly trying to find make sample to draw samples from the target posterior distributions. Well, this method is promising in the sense that it can be statistically exact, but it can be very inefficient when we have a lot of data sets, in particular when n is large and when the dimensions of our neural network is large. So our method to tackle this problem, in particular to tackle the large dimension in the parameter and the large dimension in the data set, is that we leverage two observations. First, we need to decompose a full BNN, a full Bayesian neural network, to a partial stochastic one. So precisely, it means that we're not going to put a prior on all the parameters of a Bayesian neural networks, but instead we only select a subset of all the parameters to be stochastic. Okay, this is the idea which actually came up in very recent years, because it turns out that if you only care about the prediction performance of a Bayesian neural network, so it is actually not necessary like you put prior on all the parameters. Okay, now the catch is that we will have two sets of parameters of a neural network. We got phi and psi. Now the phi will be a random variable which we put priors on, and psi will be just standard deterministic neural network parameters which we can optimize with some first order gradient-based optimizers. Now we need to decompose the neural network in a way that the dimension of phi should be significantly smaller than that of psi. Now, if we can decompose a Bayesian neural network into two parts, then we can solve the problem of large dimension of neural networks. But still, another problem is that what about if we have very large data sets? Now, to tackle with this problem, we come up with a sequential Monte Carlo method, which we can use to jointly learn phi and psi in an online fashion. Okay, so I will just basically skip every technical details. I will just directly present to you the algorithm, how to do so, and it will be very easy to implement. Now the input, suppose that we have data, okay, xi and yi. Now the output, okay, the outcome of training of the neural network will be, we want to compute the posterior samples of phi, and we also want to learn the neural network parameters to see. This will be the output of the training. Now first we want to do initialization. First we initialize the neural network determining spark parameters. Let's call it C0, and then we initially draw samples of the random part of the neural network, phi0, from the prior. And then we initialize a bunch of weights for each samples to be uniformly distributed. And then we can start to do a loop for optimize for the training. So if for I equals to 1, 2, until convergence, we do this. First, we draw a sub data set with batch size m. Okay, we draw a sub data set, and then we can resample the previous samples, the phi and the weight if needed, and I can explain what it means by resample later. And then we propose the samples. Okay, we propose the samples via a so-called Markov kernel here. Notation is HI in the line 7, which means that we want to propose the samples with certain dynamics. And then we reweight the weights of the proposed samples via the likelihood model, okay, and by evaluating at the sub batch data. And then at line 9, we just optimize our, we normalize our weight. And then in line 10, we compute the gradient by evaluating with the data and the proposed samples. And then after we compute the gradients, then we can just simply apply a gradients descent step to optimize the neural network determining spark parameter psi. And that's it. That's all of the algorithm. And here are some experiment results. toy data so that I can show you the visualization, so I can explain to you in details what is happening in the training. So here it's a simple regression problem. You can see that here the dashed line, the dashed black line is the true function which we want to approximate. And the scattered points, they are the data we have. We have some noises around the true function, so we don't have perfect measurement. Now, simple regression problem. Now, on the 5 figures are the results of the approximation by a different bunch of methods. For example, MEP, Hamiltonian Monte Carlo, and our method, OHSMC, and a bunch of other methods, variational Bayes and stochastic weights, averaging, etc. And you can see that the second figure is visibly the best, because first it can learn some very details in the middle part. You can see it can learn the very intrinsic, complex part of the function, and also it can extrapolate well of the function. Now here's then a simple demonstration of classification task. So in this figure, we have 2 classes. One class is marked by a hollow circle, and the another class are marked by solid circles. This is known as the Moon data, the Moon data sets. So we artificially add some noises to make sure that the problem is more challenging. Visibly, you can also see that our method has the best performance, and also in terms of the expected collaboration error, which we also get the best results. And if you would like to see more results, okay, like on UCI data, MNIST, or image classification, if you would like to see the concrete numbers and numerical results, you're very welcome to take a look at our paper, which you will have very detailed explanations and detailed results. And yeah, and that's it. So if you're interested in our work, you can scan the QR code to access our articles and the implementation. So thank you.
Thank you so much, John, Joe. And this was a really amazing session by you. And yeah, so upcoming and next, we're gonna have this is the first and the only double session we're gonna have in this summit. Where next up we're gonna have Terry Singh and Nardera. They're gonna be both presenting soon their research topic and presentation. So do we have on stage Terry and Nardera? Do we see you guys or hear you? Terry Singh, can we hear you or see you? Or we have next to Nardera. Okay, so since we can't see them, we're gonna mix up the times. So we're gonna have up next as, oh, we have Nardera with us. I don't know why I can't hear you guys. Nardera. Maybe unmute yourself, like on my unmute. Let me try to do it.
Can you guys hear me now? Okay, I think you. I can't hear you, but you can hear me.
Oh, sorry. Yes, sorry. Okay, can you guys hear me now? So now we have Terry and Nardera, correct?
Yeah.
All right, perfect. So welcome, guys, in the upcoming session. Well, they will be presenting about humanists designing sustainable foundation models. The stage is all yours now.
Perfect. Thank you. First of all, Haneen, thank you so much. And thank you, Super AGI Summit, for reaching out to us and sharing, with this wonderful summit that you guys are running. Thanks. So we are going to be talking about Hominus. That is a project that has been coming along for a long time. I still remember back in the days when OpenAI was still working on its GPT-1 model. I had met the team in 2017, and we were talking about multimodality. So I'm just going to give a brief introduction of ourselves, and then Narendra is going to take over from me. So this project, Hominus, in Latin, it means humanity or for humans, is a human-centered AI project that we've been envisioning for a long time. And it's a project where we are working in collaboration with NVIDIA and also with the University of Naples. That is the oldest university in the world. We have a couple of million hours of GPU where we're going to be spending this year training these models. There's been an announcement we made a couple of weeks ago. We're talking about 14,000 GPUs. So the fourth largest data center in the world, called Leonardo, in Bologna in Italy. If you move on to the next stage, next slide, Narendra, please. Thank you. So yeah, I mean, without much further ado, I'm going to pass it on to Narendra. So this is just an introduction, so you guys get to know where our vision is coming from. And Narendra is going to kind of give you guys a bit of a perspective of why we feel the need to come up with a foundation model. In Europe, you guys have already seen Mistral, just 9 months old little startup, is actually moving very fast. We still feel that a lot of big problems on multi-model foundational models have not been solved. So Narendra, the floor is yours. Go ahead.
So, hello everyone. In this paper, we introduce the notion of sustainability and programmability for foundation models. And we then provide a general recipe for making large models more suitable for downstream applications. Before going further, I would first like to introduce the concept of foundation models, although I'm quite sure that everyone present over here is already familiar with it. So, our interest in foundation model is because they provide a common frontier for AI development, as opposed to more traditional way of developing custom models for each task. Gen AI has been transformative force for AI, and models based on transformer architecture has made impressive strides in the domains such as NLP or computer vision and robotics. The permutation invariance of transformer layer has been essential for making them suitable for processing arbitrary length sequences and making them viable for processing on modern GPU based accelerators. This in turn has made them well suited to be pre-trained on vast amount of data and be usable as a backbone for downstream applications. The deep learning community has coined the term foundation models to denote any such large models that have been trained for this purpose. While foundation models exhibit a certain emergent property with scale, its ability to generalize to novel sequences, over the past few years, the over reliance on scaling has caused a certain stagnancy in AI research. So, as you can see, over the last 6 years, the size of models considered to be foundation models has had significant increase in number of parameters, almost exponential. However, simply relying on scaling up has led to diminished returns as well as overfitting that can be seen by the scaling laws. While foundation models by definition are supposed to be something that other people can build on, this high parameter count has restricted their use from broader audience. And thus, to a certain extent, the focus has been rightfully shifting towards other avenues of improvements. In addition to the sheer size of the data sets and the model parameters, the sheer size of data sets makes it kind of impossible for human beings to manually check the data present within the data sets. And so, what the effect of that is that it magnifies the biases and toxicity already present in data sets and makes it trickle down in the downstream applications. There are many commercial like foundation models such as GPT-3 or GPT-4 that have shown that they regurgitate the copyrighted material from New York Times. Or for example, Copilot regurgitates the material from privately held repositories. This lack of data curation in pre-trained stage leads to suboptimal generative capabilities. And thus, the downstream refinement needs more curated datasets. So, before going further, based on these identified problems, we managed to provide solutions in two-part. So first, we look into the sustainable modifications within the transformer block, and then we look into how to arrange these blocks to have a grander architecture that is more suitable for downstream use. The attention mechanism, as mentioned earlier, forms the core of transformer architecture. Thus, there has been a tremendous effort invested in finding alternatives that can process the same like attention matrix using less compute. The majority of these effects are concentrated in finding linear approximations for the attention matrix. In this paper, we conduct ablation studies on three different attention variants: flash attention, which is a hardware-specific acceleration method; linear approximations, in which we choose the three like top performing variants, which are reformer, informer, and longformer; and synthetic attention, which proxies the attention matrix by handwritten rules. And what we found out was that hardware aware acceleration performs better both in terms of training as well as inference time. So, uh, the metrics that we used to compute this were wall clock throughput and attained perplexity. While attention forms the core of the transformer models, majority of the parameters within the transformer block are held within the linear projection layers. In the second set of ablation, we replace the linear layer with a parameter equivalent MOE layer, and this switch resulted into better perplexity with lower inference time. Next, we move on to sustainable modifications to model architecture itself. While most of the popular variants follow a decoder-only repetition of transformer block, primarily due to ease of training, encoder and decoder models are more suitable to capture longer context. And as we go forward, capturing larger context is becoming more essential to downstream applications. We thus propose a novel recipe for training large language models that is based on four core pillars. First is pluggable decoding. By decoupling the training of encoder and decoder parts of the transformer, we retain the faster training advantages of the decoder only models and then retrofit the encoder on top of it with limited data. The second is universal tokenization. A significant part of model parameters is based in the embedding matrix, and that embedding matrix itself cannot be loaded on most of the consumer facing GPUs. So, an alternative that we propose for this to reduce the compute required is to just use byte-based tokenization, which significantly reduces the embedding matrix size and at a slight cost of adding more attention layers. By directly processing text as bytes, we reduce the storage by a large amount, and we also make it more attainable to be extensible by multimodality. Okay. The next one is intermediate representations. So we rely on cross attention to decouple the size of context length from the generation time required. Because decoder only models process one token at a time, if the size of context is higher, then the generation time is also higher. Whereas by decoupling with cross attention, we completely remove that and have a constant generation time. We also found that by using post hoc retrieval augmentation, with LoRa matrices, allows hot swapping of the information held, and performs quite well for downstream applications. While the experimentation for this model was done for a smaller dataset that we privately curated, which was again permissive, the scaled up variants of the proposed model are under training using the ISCRA B grant that Tari earlier mentioned, and we would be making several releases in the coming few months for the data set itself as well as the permissively licensed model variants in both raw and instruction tuned forms. So if you have any questions or want to be part of this effort, then please reach out to Tari at this provided details. Thank you.
Perfect. Yeah, just to conclude, Hani, thank you so much, Narendra. So you guys have seen that we are as we speak, we are training this large language model on the fourth largest data center in the world. In the next couple of weeks, our first model we're going to be releasing as per the European Commission's also requirement. We're going to be open sourcing these as well. There's an app store we are working on, so we are obviously very excited to talk to people. If anyone of you is interested, you can always reach out to us. We can tell you a little bit more. There's a lot of work under the hood, which we obviously cannot talk about. But once the first model is released publicly, then you guys are gonna get a much bigger sort of overview of how we are designing this. Thanks everybody, but thanks again, obviously Super AGI. I know there might be questions, and you have, I guess, a session left for questions. We're going to wait here and patiently after the sessions are over, and happy to sort of talk to folks and connect with you guys. Thank you once again. We are very grateful.
Thank you so much, Terry. And I am for sure gonna reach out with this amazing session and this amazing insights, and can't wait for what you guys gonna bring. And just
Thank
for
you.
clarification, in the panel you will find Q&A sessions where you will have people are asking their questions there, and also in the live. So really, thank you so much for this amazing session.
Thank you very
Have
much.
a wonderful day. So upcoming and next, we will have our next speaker, which will be John Wang Sung. John Wang Sung, I hope you're with us now on stage. Let me just put you. And yeah. Are you with us, John Wang?
Yeah, I'm here.
Hi, nice. Hello, dear.
Hello.
How are you?
I'm fine, thank you. How are you?
Good?
Yeah.
It's nice having you. So now the stage is yours, and
Okay.
can't wait to see what you have.
Right. Good evening, guys, and my name is Chunwon Sung, and it's great to introduce our research to you guys. And currently, I'm developing AI-based solutions for EG asset pricing, and I deeply appreciate your presence here today. If you guys have any questions during the presentation, please do not hesitate to post them in the session chat. Our team members are present in this session and will be able to answer those questions, or contact us at the email address listed on the last slide. I hope this session provides valuable insights, and let's get started. Before diving into content of our paper, I'd like to briefly introduce what our company, EG Asset Pricing, does. It provides financial valuation in bonds, derivative products, and alternative investment assets. In response to changing times and technological advancements, we have been focusing on expanding financial information services through AI technology. Our goal is to support our clients in making more accurate and effective investment decisions in the market. Let's move on to the next slide, which is about the background of our team research. Traditionally, financial analyst has been a labor-intensive process, requiring extensive readings, interpretation, and summarization of financial documents to make decisions. However, the advent of LLM presents an opportunity to revolutionize this process. We believe the LLM's ability to understand and analyze natural language at scale. This enables it to extract meaningful insights from financial texts much faster than a human analysis. However, this new technology is not without its drawbacks. Despite its numerous advantages, we have also identified inherent limitations and challenges associated with LLMs. The first issue from our study is a discrepancy in sentiment scale between human evaluations and GPT assessments. A human use a mix of culture context, emotional intelligence, and personal experience, leading to a nuanced and sometimes subjective interpretations. GPT models, like while adept on identifying statistical patterns, may not always interpret GPT models while adapting identifying judgments correctly, resulting in potential discrepancies. The second issue is the sentiment analysis inconsistency. This variability within even a single document, highlighting the difficulty in achieving uniform sentiment analysis, influenced by language complexity, domain-specific terminologies, and texture structure. Such inconsistency is problematic in decision-making contexts where consistency sentiment analysis is crucial. Lastly, the LLM outputs are often hard to interpret, so it's kind of the black box problem. However, in fields like finance, clear explanations for system outputs are strongly required. The lack of transparent explanations can harm trust in LLM-driven analysis and limit their use in contexts requiring interpretability. Our aim today is not to present definitive solutions to those issues, but to share our experience and the challenges we've faced. We hope to initiate a dialogue on addressing these problems, emphasizing the development of methodologies that can bridge the gap between human and machine sentiment understanding, enhance analytical consistency, and improve output interpretability. Let's get into the content of our research paper. Our study, we used the corporate disclosure as the main source data. These disclosures come in two types, which is periodic and continuous. Periodic disclosures are routine reports, including financial statements and quarterly updates. On the other hand, the continuous disclosures, which is current disclosure also, cover significant information that emerges outside the regular reporting schedule, such as merger announcements, change in executive leadership, and rights offerings. These documents are crucial for our monitoring system, given their potential immediate impact on the stock prices and the necessity of alerting shareholders. Our research revolves around two main questions. First one is how effective are large language models, especially GPT-3.5 and GPT-4, in analyzing sentiments? Second, what are the challenges or limitations associated with using these models for sentiment analysis? Through these questions, we aim to provide a comprehensive view of both capabilities and limitations of large language models in sentiment analysis. For our data set, we selected 50 companies listed on the KOSPI and collected all their current reports from January 2022 to May 2023. The disclosure were first summarized into a single sentence using the GPT-3.5 model. This data was systematically converted into a monthly time series format for effective sentiment analysis. As illustrated in the given table, each data point includes the key elements, such as you can see on the table, there's a date, time, title, and summary. With a collection cap of 15 disclosure per month per company. We did that because the content GPT can host, there's a limit of the tokens. In our experience, both GPT models and human evaluators were given 815 evaluation queries, Scoring feature stands on a scale from 1 to 5, which is very negative to very positive. For human evaluation, we collaborate with two experts with over 10 years of experience in financial data analysis, using the same criteria of assessment as the GPT models. From the two human experts, we averaged and rounded down to an integer to serve as golden standard data. In this slide, we present an example of how scores were assigned and the rationale behind the evaluations, offering insight to the decision-making process. Before examining the performance table, let me explain the 4 conditions that under which the analysis was conducted, illustrated with graphs. The first condition is the baseline, as you can see on this graph, with no specific adjustments. When you look up the condition 1 graph, this distribution of rating score between human and model is unbalanced. The green one is the human, the blue and orange one is the models. The second condition explored the hypothesis that model ratings might be biased towards positively. Here we also observed a notable difference in scoring, especially with GPT-4, which tended to rate more positively. By adjusting scores above 4, deducting 1 point, we found that the results closely align with human evaluations. So when you look up the condition 2 graph, you can see the aligned with the human evaluations between the GPT models. The third condition hypothesis, a potential negative bias in GPT evaluators. Returning to baseline, we can see we noticed that negative ratings were similar to those of human evaluators. Adjusting scores below 2 by adding 1 point resulted in a skewed graph. You can see that on condition 3 graph over here. The fourth condition applied both adjustments, which is condition 2 and 3, demonstrating a significant shift in data distributions. Across all test conditions, GPT-4 consistently outperformed GPT-3.5, showing higher correlation coefficients in every scenario. Remarkably, its performance under condition 2 set a new benchmark, adjusting GPT scores particularly by deducting a point of some scores over 4 significantly improved model accuracy. The adjustment was especially effective for GPT-4, jumping from 43 to 82% agreement rate. This indicates a systematic positive bias in GPT-4's ratings, underscoring the importance of critically assessing and recalibrating GPT outputs. And this is one of our future works for our own FedWatch service. For that, we collected FOMC tax data for the last 10 years. From the attempts, we obtained many positive results, but I'll show you guys just one result from the slides, FOMC statements data. As you can see in the graph, the contents blue dots are feather rates, and the orange ones are our Dove and Hope ratings ranging from 1 to 5. Here, rating 1 means a favorable stands toward low interest rates, while 5 means that it shows its preference of higher interest rates. Please note that the ratings are moving averages of the time window of length 4. To our surprise, it clearly shows that the change in ratings precedes the pattern of the Fed interest rates. If you're an active investor and watching what you have to watch at FOMC meeting last month, the attitude of the event was quite hawkish, meaning that the FOMC members were not likely to lower the interest rate at any time soon. As you can see in the graph, the last sentiment mode score slightly goes upward, which strongly agrees with our intuition. However, the graph is very rough, and there is also consistency issues with the ratings. We observe that there is a randomness in the sentiments rating for the same prompts. Fortunately, the randomness seems not random and kind of a central tendency exists in their generations. These kinds of problems are very common when you apply LLMs like GPTs to sentiment analysis, but it'll be a shame not to use this technology because of these problems, since we will find ways to deal with them. In conclusion, our research demonstrates a potential of large language models, particularly GPT models, in revolutionizing sentiment analysis of corporate disclosures. While we've uncovered significant capabilities of our findings, also highlighting the critical needs for careful evaluations and adjustments of these models to ensure accuracy and reliability. The challenge we've encountered reminds us the importance of balanced approach. Blending AI innovative power with human expertise, as we move forward, our goal remains clear: to refine these tools for better financial analysis to decision making. Thank you for listening to the research, and we look forward to exploring this promising find together. That's it.
Hello, hello. So thank you so much. I'm sorry there was a bit of technicality with it. So thank you so much, John One, for this amazing
Yeah.
session. Pretty insightful. So it was great having you here today. Thank you.
Yeah, thank you too.
Thank you. So upcoming next, we're gonna have our last but not least speaker, and we have upcoming next Aniket Reggie. So let me put you on stage, Aniket, and uh, also John One. I believe you have to close your stream. If you can please stop sharing your screen. Yeah, perfect. Thank you. So Aniket, how are you?
Hi, I'm doing well. How are you? Can you hear me okay?
I can hear you perfectly. How is
Awesome.
it going over there?
Oh, pretty good, pretty good. It's a nice sunny day, so
I
it's
can
going
see
pretty
that.
well.
That's nice.
Yeah.
It's already night over here, so
Oh, good.
yeah. So I'm gonna leave the stage to you and everybody.
Sure.
Aniket Reggie on stage. Thank you.
Awesome. Yeah, thanks, Anine. Let me just share my screen. Um, all right. Hi, everyone. Thanks for joining this talk. So I'm gonna be talking about my research paper from last year called ADANS, a framework for adaptive semantic search. This is work that I did at the University of Washington with collaborators from Google and Harvard. And let me go ahead. So this paper is primarily talking about search at web scale. So think of what Google does, basically. And so typically nowadays that involves a neural encoder. So which is usually some kind of transformer like BERT, which encodes our data into a d-dimensional dense representation. And we can do a nearest neighbor search on top of that for any query that we might have. And usually this is in very large databases, billions or trillions of data points. And the data dimensionality is usually in the hundreds. Okay? So this pipeline has numerous challenges. First of all, the scale of the data is hundreds of terabytes, and our complexity scales linearly with time, and with the dimensionality d. The neural encoders that we typically use that are transformers are very expensive to train. They cost millions of dollars to train GPT models and vision transformers at Google and so on. And the embeddings that we get from these models are rigid in the sense, what do we do if we want smaller embeddings or slightly larger embeddings? There's no sense of multi-granularity, so we can't flexibly use any size that we want. And finally, the actual search index that we build on top of our representations is built sort of after the network has been trained and after we get the representations, and so it's post hoc. And so it's not sort of learned alongside the representations. Okay? So there's a bunch of challenges. And, the question that we try to ask is, can we use some kind of flexible or adaptive representations to solve some of these problems? And that's where Matryoshka representation learning comes in. So if anyone has been following OpenAI's latest embedding models, this is the method that they use to train their latest embedding models. This is one of my previous papers from 2 years ago. So basically, all that it does is to solve the same learning task at multiple stages. So if you're familiar with the concept of Russian dolls or Matryoshka dolls, you have a bunch of dolls that are sort of nested within other dolls. So you have a small doll here, which would be the sort of red box that sits inside a bigger doll, which is the orange box, and so on. And all of these dolls or boxes are representations. And the way that we learn these is to just take a loss across all of these scales and just add them up together. So that's a really simple overview of what Matryoshka representations are. And this is a nice little GIF from a recent Hugging Face blog, which shows, for this query, the weather is so nice. We pass it into a neural network, and we get a 1024 dimensional embedding naturally. And what we can do is to truncate that at whatever size we want. Okay? So we don't have to stick to 1024. We can pick 256 because that's the size that fits in our budget. So that's an illustration of that. And another sort of simple example is for this query, which is, it's so sunny outside, which it actually is from where I am. If we pass that into an embedding model, we get this 1024 dimensional embedding. And because this embedding has been learned with Matryoshka representation learning, we can just chop it off at whatever size we need. Okay? So that's the sort of representation learning paradigm or pipeline that sort of powers a lot of the work that I'm about to present. So what is this concept of retrieval? So this is basically akin to what Google search is doing. So we have some query that we have, we want to search for pictures of a cat, and we want to get the most relevant images from a database, which is Google's indexing the internet, basically. And so what we did in this work is, for images, we trained ResNet 50 models on ImageNet. And for text, we fine-tuned BERT on natural questions, which are both sort of large, million-scale data sets that you can see here at the bottom. And usually these things are evaluated with something called mean average precision, which just tries to see, how accurate can we get when we retrieve, 10 relevant items from our database. How accurate are we at each scale from 1 to 10? And so now what MRL lets you do is to do this retrieval adaptively. So what you can do is, you start out with a database of size n, and you can use a small dimensional embedding to get a large short list of candidates. So you have 1 billion images, and you use only 8 dimensions to get 1,000 candidates with approximate search. And maybe you get 200 documents from that. And what you can do then is to just freely re-rank those documents. So you reorder the documents with a higher dimensional embedding. So you get sort of the best of both worlds of high speed with a lower dimensional embedding, as well as high accuracy by just re-ranking them. And this is actually really cheap to do because both of these, the red embedding is sort of just nested within the larger one. So you can just truncate it or slice it off to get the smaller one for free. And your re-ranked documents are the final thing that you have. And so this is a sort of simple application of that. So this is showing for the query, what is a panda, over this text corpus here. What happens if you change the embedding dimensionality from the highest, which is 768, all the way down to the lowest? And you can see that the best hit, which is a panda is a large black and white bear native to China, that sort of stays consistent no matter what the embedding dimensionality is. So you can see that you can get away with using, instead of using 768 dimensions, you can get away with just using 64, right? Which is a huge sort of saving of your embedding size. So finally, I'll move on to this actual work that I'll talk about, which is adaptive ANNS. So that's basically saying, can we add this kind of flexibility that MRL gives to the actual search pipeline itself? Okay, so can we add adaptivity to the components of search and not just the representations? So that's the sort of broad question that we asked in this work. So I'll walk through what that means. And so for a sort of standard search pipeline that Google may use, they may have 1 billion points and learn 50,000 clusters over those points. So it's kind of like a tree structure. And let's say we cluster those with 128 dimensional embeddings. And then within those 50,000 clusters, we would have our 1 billion points split into a bunch of documents for each cluster. And then, once we get a query, we would find what are our best clusters and then only search the documents within those clusters. Okay? So this is a sort of standard setup. And the caveat here is that you have to use the same dimensional embedding for every single stage here. Whereas with, adaptive representations, what you can do is you can have a larger number of clusters with a smaller data embedding because, it's the sort of same cost. So you can half your data embedding to 64 and double the number of clusters, and you have the same sort of cost for that. And then what you can do is shortlist the clusters with 64 dimensional embeddings, and then you can do your linear scan again with 128. So you actually save a bunch of cost in your first stage because you're using half the size of your embedding. And so it turns out you can actually get really good performance if you do this. It's just that without adaptive representations, this wouldn't be possible because you would have to have multiple copies of your database, multiple indices, multiple inference passes, so it would get very, very expensive and slow to do this. And so I'll come on to some of the results that we had. So on the left side, this is, on the x-axis, we have your actual search latency, so how long it takes to search a query. And on the y-axis, we have the actual accuracy. And this is with a tree structure, so IVF is a tree structure. And what we found is that if you use this kind of adaptive representations to to decouple the representations you use at each stage of your search, you can get up to a 90 times real world speedup in actual inference time, as well as a 1.5% gain over in accuracy. And we also tested this for something called OPQ on natural questions, which is basically a quantization technique which makes your distance computation cheap. So it basically means when you're actually searching a cluster for what your best relevant documents are, you don't actually compare your 128 dimensional embedding to all 128 dimensional embeddings in the cluster. You quantize everything and you approximate those distances with quantized representations. And it turns out if you do that with our setup, you can get a 2 times cheaper quantized budget. So you can get away with using 32 bytes instead of 64 bytes for the same accuracy. Or if you want to go with 64 bytes, you can improve your accuracy by 3%. And this is, again, going in a little bit more detail about that quantization aspect of it, where we tried this with the blue line is with our method, and the red lines are with sort of status quo methods that don't have adaptivity. And basically, this is showing that if you have a fixed compute budget for any kind of vector search or retrieval pipeline, if you use our method, you can actually get substantial benefits in small compute budget regimes for free, essentially. And we also tested this out by combining a bunch of different components of approximate nearest neighbor search. And so typically, those are split into sort of coarse quantization techniques where you partition the search space. So you have things like trees that I talked about earlier with IVF, and you also have graphs. And so typically how this goes is, trees or IVF is used by Google, DiskANN is used by Microsoft, and HNSW is used by Meta. So each, sort of large company has a different technique that they use to partition the search space. So you're not searching everything, you're only searching sort of promising regions. And then your fine quantization is just, when you actually find the regions to search, you're actually searching them with approximate distance computations and not sort of full precision distance computations. And so we showed that no matter what combination you use, we typically get really good benefits with our adaptive technique, which are the blue lines that you see here. Finally, I'll move on to some limitations. So one limitation of doing this is that there is a one-time cost of training a neural encoder with Matryoshka representation. So you need to train this once, which can be expensive. But again, it's just a single training cost, single time training cost. And another caveat is that optimizing for dimensions that are very, very low can hurt high dimensional embeddings. So if you go too low, it's very hard to learn very, very small representations that work well. And so you have to be a little bit careful there. And the future of this is you can, a lot of people have been releasing open source implementations of MRL lately. So Sentence Transformers, for example, has an MRL implementation. OpenAI just came out with embedding models that have MRL functionality within them. Well, they're not open source, but they're available. And you can also do interesting things like optimizing for different things that you care about at different scales. So you can have high recall at low dimensions and high robustness at high dimensions. And then finally, you can also learn a kind of search structure on top of this sort of adaptive ENNS pipeline, which means that you can basically the pipeline will basically tell you what the best embeddings to use for your task are and automatically use them to build your structure in search. And so that's the sort of future direction that we're looking into. And finally, if you want to know more about matryoshka representations, I have a recent blog that I wrote that sort of walks through what they are and how you can use them for search and for anything where you need learned representations. And you can also get in touch with me at my Twitter, and I have some threads there. And yeah, that's pretty much it. Thank you all for attending.
All right, thank you so much. Thank you, Aniket, for this amazing session. And make sure to also follow him on Twitter. So yeah, thank you so much. And hope to see you again at the closing ceremony. And
Thank you.
everyone, thank you, dear. And moving on, we're going to have our last session for today's Reasoning and Intelligence Summit session. And next on, we're going to have Dong Zan. I hope I spelled your name correctly, Dawn. Is Dawn with us? Let me try. Oh, yeah. Dawn, you with us?
Hey, hello. Can you hear me?
Here. How are you?
I'm fine.
Good?
Yes.
I love the background. So yeah, so everybody, Dawn is on the stage with you guys. So enjoy and have fun in our last presentation.
Okay, thank you. Let me check. So today I want to talk about our work about how to build a large speech language model, and that is our speech GPT serious work, and I'm Dong Zhang from Fudan University. And today I want to briefly introduce our three work, that is speech GPT, accepted by EMLPX 2023, and speech together, accepted by ECLAIR 2024, and the speech GPT Gangjin, that is our new preprint in 2024. So since 2023, the ChatGPT comes out as a super chatbot, having great text understanding and generation abilities. So, but however, speech is the most is a more common way a way of human communicating with each other. So, let's see the speech enabled large language model interaction. They are most consist of one cascaded spoken LLM, which is a pipeline system consisting of whisper, ASR model, a large language model like ChatGPT, or a text-to-speech model. And here are many products like this. However, they have weakness like error accumulation from this pipeline approach, and they lose the speech paralinguistic information like speaker, like timbre, like the background noise, like the emotion, and they also have a high inference latency. And they also lack of the support for this unwritten language models, which does not support. So because speech is another modality for larger models, so we can see what current multimodal larger models do. So multimodal large language models, they are mostly of them are like this. They consist of two parts: modality-specific encoder and large language model. So due to this architecture, they can only take the multimodal signals in and output the text output. So the drawback is that the lack of the multimodal generative ability, and naturally, we could have let's see what's the gap between the general modalities and the current large language models, and the for the general modalities, we often represent them as continuous signals like image or sound or even ECG signals that continuous signals. However, for the large language model, they take the discrete tokens as an input and output. So I think the continuous and discrete are the main gap between them. So naturally, we could have this stance. Can we represent the continuous signals as discrete tokens? This is our first motivation of our work. That is represent the continuous signals as discrete tokens. So here comes out the first work called the Speech GPT, empowering large language models with intrinsic cross-model conversational abilities. So let's first introduce the speech discrete representation. Here is an introduction of this. We can discrete the speech into the discrete units like just like this, we discretize the speech through performing k-means on the representation of the nice transformer layer of this Hubert model. And just like this, a speech signals takes into the CNN encoder, and the transformer encoder get a continuous representation, and we perform k-means on clustering on this, and we get these discrete labels. So to here, we could view the speech discrete representation as a new foreign language for the large speech language model, because they are both discrete tokens. And this is the model structure of our speech GPT. It consists of three parts: the discrete speech unit extractor, and the large language model, and the unit encoder. The core architecture here is a language model, which it could take the discrete speech representation as input and output the discrete speech representation. So for the speech GPT training, it can be diving into the four parts. The first is the implementing vocabulary. We need to take the speech discrete representation into the vocabulary of the language model. And the second part, for the training, it consists of the modality adaptation pre-training, cross-model instruction fine-tuning, and the chain of modality instruction fine-tuning. So I will not introduce this part in detail due to the time limitation, but they are almost the same as the common training process of the large language models. So I think we could listen to the demos of our speech GPT here. So here we speech GPT can perform cross-model instruction following and the spoken dialogue. So for the cross-model instruction following, we have instruction like, can you transcribe the speech into a written format? We have input here. And it generates the transcription of this input. It can also perform text-to-speech tasks. and it can even perform spoken dialogue, like we give him a speech instruction, like what are the 3 primary colors, and it can generate speech output. Just like this, so it can perform speech-to-speech dialogue, and I think this is amazing. And you could listen to more samples in our demo website. And okay, so and however, we found that SpeechGPT can support more speech tasks related to paralinguistic information like the speaker recognition, emotion recognition, and we couldn't control the timbre of its speech response. So what caused this? And we think is the speech tokens. The speech tokens obtained by Hubert lose a lot of speaker information, emotional information, and paralinguistic information. So here comes out our next step. We could build a better speech tokenizer. So here comes our second work, speech tokenizer, unified speech tokenizer for speech language models. So here we could have briefly introduce our current speech discrete representation for the speech token semantic. The first is the semantic tokens, which like Hubert will direct BERT. So the architecture is transformers, and they are often trained by massive learning remodeling or constructive learning, and they contain the long-term semantic information. For the acoustic tokens, is the second tokens, and they like Soundstream or encodec. They are residual vector quantization GAN architecture and the CNN-based encoder decoder. They are often trained by speech reconstruction, and they often contain more detailed information about the speech, like we call it acoustic tokens. So for our speech tokenizer, we hope to just like this figure, the Hubert and the semantic tokens contains the content information, and the acoustic tokens contain the mixture of time, just like this, content timbre and acoustic details. And for our speech tokenizer, it can produce the unified token, which the first RVQ layer contains the content information, and the second to last RVQ layer contains the timbre acoustic detail information. So here is the information entanglement here. So we achieve this through multitask training, like we perform speech reconstruction task for the 8 RVQ layers, and we perform the semantic distillation for the first RVQ layer. So through this multitask training, and we could achieve and we could get a swing to like this, and which performs information entanglement across different RVQ layers. So here comes our demo, and I think we could list to one. So this is the result speech, and this is a speech reconstructed by the first RVQ layer. We can hear it is more like a robot speech this work. And this is so from this speech we couldn't hear what he said, but what the content is, but we can just conclude that it has the same temper as the raw speech. So this is the a reconstructed speech. We could have it is almost the same as the raw speech. Okay, so based on the speech tokenizer, here comes our work called SpeechGPT Chain, scaling chain of information speech generation. So first, I will introduce our core design called the chain of information speech generation. So let's see this figure, and for A and B, and they are all speech generation method and consist of two stages. A is integrated modeling. For the integrated modeling, the first stage performs the mixture modeling of speech. They models the semantic and the perceptual information at the same time. And for the second stage, it is also the same progress. And for the content entangled modeling, and the first part performs the semantic information modeling, and for the second part, it conducts the semantic and the perceptual modeling at the same time. And so here comes out our design chain of information modeling. And for the first stage, we perform the semantic modeling. And for the second stage, we perform the perceptual information modeling. So there is also an information entanglement design here. So our GPT consists of two parts. The first is a large speech GPT called a large language model for semantic modeling. We perform the speech semantic modeling by a powerful ability of large language model. And the second part called the flow matching for perceptual modeling. So we use a flow matching method, and which is a non-auto-regressive generation speech generation method, and it is proposed in VoiceBox from Meta. So here comes our main results. From this table, we can see that speech-GPT engine performs well in text-to-speech, voice conversion, and speech-to-speech dialogue. So and here comes the last analysis. I think it's an important analysis that the chain of information. We prove that chain of information is efficient and effective. We compare the chain of information generation method with the integrated generation and the semantic disentangled model, semantic disentangled generation from model convergence and the downstream performance. So from this figure, we can see that chain of information generation, which is blue, it achieves the fastest model convergence and with the lowest training loss for both autoregressive and non-autoregressive modeling. And for the downstream zero-shot text-to-speech, and we can it also achieves the lowest word error rate and the highest speak information, which proves that chain of information is efficient and effective. So here is a demo, and we can. So this is the speech instruction, like what are the main causes of climate change. This is a prompt speech, which just we let the model to give the speech response in the timbre or in the voice of this prompt speech. So we can hear that it gives the correct speech response with the voice like of this prompt speech. So we can conclude. So here comes the conclusion. We propose SpeechGPT, the first conversational speech large language model. We also we propose Speak2Ladder, the first unified speech discrete representation extractor. And based on this, we propose SpeechGPT engine and a semantic and a perceptual disentangled modeling model. So if you are interested in your work, feel free to contact me, and our SpeechGPT have earned 800 stars in GitHub, and Speak2Ladder had also earned the 2050 stars in GitHub. And this is our personal page, and you can contact me through my email. So thank you for your listening.
Thank you so much, Don. And it was amazing to close this amazing session with your last presentation. I hope everybody enjoyed as much as we did. And so, everyone, it was such a beautiful day and a great start of the day to have this amazing research and amazing like presentation brought by all of you. And now we have our closing ceremony that's going to come up next. It should start now, I think, in the next 2 minutes. So please watch us over there in the closing ceremony for us to present our top 6 researchers who made it showcasing this AGI Leap Summit. And yeah, see you there. And it was great having you all. Bye bye.